Kim, and I'm the first author from Korea University. I'm going to present our work. Let me get started. Recently, a mobile method, 3D-GS, has been proposed which uses 3D Gaussian functions, enabling highly detailed and photorealistic rendering. Tools such as Unity can support 3D-GS. As shown in the figure, using Unity, 3D Gaussians can be rendered in VR application. However, computational cost of 3D-GS can be challenging in resource-limited VR environments. 3D-GS obtains the 3D point cloud of the scene with COMAP, which uses SIFT. Figure on the left shows the 3D point cloud in green dots generated with COMAP. Majority of 3D points are located at the edges and corners. A Gaussian is initialized at each 3D point, and figure on the right shows the optimized Gaussians. They are downscaled and painted green for visualization. Unlike initial 3D points, it can be observed that the optimized Gaussians are well distributed. Therefore, during optimization, Gaussians are shifted away from the initial position. However, this drags convergence of the optimization. Also, the number of Gaussians has been increased during optimization by the density control. However, this also increases the usage of memory, which makes it difficult to render the realistic scenes in VR. In order to tackle such a problem, we propose superpixel guided sampling for compact 3D Gaussian splatter. As shown in the figure on the left, our method produces sparse but well-distributed 3D points. A Gaussian is initialized at each 3D point, which is located already away from the edges and corners. Therefore, during optimization, Gaussians are shifted far less than 3D-GS. Also, we have fewer empty spaces and the need for densification is reduced. This enables our method to reduce the number of Gaussians with similar data size and shorter optimization time. Our goal is to make a compact Gaussian representation of the scene. In order to achieve the goal, number of 3D Gaussians is reduced while preserving the rendering quality. Sharing the same goal as our method, two methods are selected as the baselines, compact Gaussian and light Gaussian. This figure visualizes the performances of our method and two baselines. It is clearly shown that our method achieves comparable 3D-GS scene quality while using notably similar number of Gaussians. Let me introduce how we achieve this goal. The figure provides an overview of our method. The input is a sequence of frames where each frame is a pair of RGB image and camera pose. We first select the keyframes. Then, for each keyframe, superpixel guided sampling is performed to generate the 3D point cloud. The 3D Gaussians are initialized at the 3D points and then optimized over iterations. We take a keyframe structure which is commonly adopted in SLAM systems. A frame is taken as a keyframe if its camera pose is notably different from the last keyframes. For example, 0.4 radians for the orientation disparity and 0.5 meters for the position difference. Then, for each keyframe, superpixel guided sampling is performed to generate a 3D point cloud with 5 steps. First, an input image is decomposed into superpixels. We adopt SLIP method for its speed and efficient memory usage. When a 3D Gaussian is projected onto the image plane, the projected Gaussian's shape is elliptical. More generally, it is convex. The figures shows two examples of SLIP superpixels with different parameters. As the superpixels presented on the left are mostly convex, they would suit better our goal. By controlling the parameters of SLIP, we make the superpixels as convex as possible. However, unnecessarily many superpixels are often generated. For example, see the ceiling area in the figure. It is mostly textureless and therefore does not require so many superpixels. In order to reduce the number of initial Gaussians, we combine adjacent superpixels of similar colors. the combined superpixels are visualized in the same color. Unfortunately, such a combined step may produce concave shapes. In order to resolve this side effect, we approximate each concave shapes by a polygon, and then decompose it into convex polygons. Such convex decomposition may often result in too many fragments. We then replace them by the original superpixels generated by sleep. The figure shows the result where the convex polygons are given the blue centers and the sleep-generated superpixels are given the red centers. An RGB color is sampled from each center and its depth value is sampled from the same position of the depth image. The depth pixel is back projected into the world space using the camera pose. Then, the figure shows the resulting 3D point cloud. 3D Gaussian will be initialized at a point. The initial Gaussians are well distributed. After this initialization, the 3D Gaussians are optimized over iterations. This video shows the optimization of Gaussians. Since the initial Gaussians are well distributed in our method, less density control is required compared to the original 3D GX. In the experiment, 8 scenes contained in replica are used. The optimized scenes are rendered using a PC with NVIDIA RTX 3090 Ti GPU. The method denoted as hours without densification is a variant of our method. This variant does not make the density control at all. Therefore, it optimizes quite a small number of Gaussians, resulting in very low computational costs. Nonetheless, its rendering qualities are not much lower than those of the other methods. This video shows the result with NeRF synthetic dataset. Our method demonstrates comparable rendering quality while significantly reducing the number of Gaussians. In this paper, we proposed a method which produces a set of sparse but well-distributed Gaussians. This method generates compact 3D Gaussians, reducing computing costs successfully, which is especially beneficial for VR environments. The experimental results show that we can achieve rendering quality comparable to the baseline methods while reducing computational costs. Thank you for listening. If you have further questions, please